Welcome to Mount Tam Astronomy, a summertime lecture series normally held in Cushing Memorial Amphitheater on Mount Tamalpais, north of San Francisco. I'm Tucker Hiatt, founding director of Wonderfest, the Bay Area beacon of science. Please join me now for another enlightening astronomy program. Just as Earth has an atmosphere, and stars, like the Sun, have coronas, galaxies are embedded in invisible halos of atomic gases. As galaxies evolve, these gaseous halos exhibit many interesting phenomena similar to rains and droughts on Earth. What do these enormous galactic climate systems look like? How are they studied? And how do they behave? Now, postdoctoral scholar Dr. Yong Zheng of the UC Berkeley Astronomy Department will give us a climate report on the largest of scales as she presents Galactic Weather.
Hi, welcome to the Milky Way Weather Station. I'm your host, Yong. In the past million to billion years, our Milky Way and other galaxies that are similar to the Milky Way have experienced many interesting weather conditions. For example, we have seen clumpy clouds floating around in the galaxies with a temperature at about 18,000 to 1.8 million Fahrenheit. There were also heavy hydrogen rings in the galaxy with a temperature that is slightly cooler but still very hot than what we have experienced on Earth. And then finally, we might see galactic winds. And astronomers have observed this kind of winds to be moving at a very high speed, at a speed that I will tell you later on. And it is much faster than what we see on Earth as well. So the questions I will encourage you and encourage everyone to keep in mind when listening to the rest of my talk are, how did these weather conditions happen? How have they impacted the Milky Way in the past, right now, and in the future? And then lastly, what does the galactic weather look like in the next billion years? And where do we go from here to there? So with these questions, now let's begin tonight's talk. Again, I'm Yong. I am a postdoc at UC Berkeley, and I study the formation and evolution of galaxies. In particular, I am interested in understanding the weather system in a galaxy like the Milky Way. The term galactic weather is a concept I borrow from the weather system on Earth. So this is not something I actually use in my research when I communicate with my colleagues. In reality, when I do research, I use a different term which I show you in parentheses here. It is called the Galaxy's Baryon Cycle. The baryon here means particle that is heavier than an electron. As we will see very soon, the galaxy's baryon cycle is very similar to the weather system on Earth that we experience from day to day, even though the numbers are sometimes could be very small or very big. All right, before we move on, I would like to tell you one mathematical concept, which is scientific notation. In astronomy, we need to deal with many astronomical numbers, and they could be really, really big, or they could be really, really small. So these numbers could be difficult to remember, and it could be difficult to communicate with other people. For example, let's take a look at this number. So I'm going to spell it out here. This number is 300000000. 0000000. So there are in total 15 zeros behind 3. This number is clearly too big for someone to remember easily. With scientific notation, we can write this number as 3 times 10 to the 15, where the 15 means there are 15 zeros behind 3. So this is an easier way to remember a big number like this. And such big numbers is very common for astronomers in their research. On the other hand, there could be numbers that are very small to remember. For example, now let's take a look at this number. This is 0.0000003. In total, there are 7 numbers behind the decimal point. In this case, with scientific notation, we can write this number as 3 times 10 to the minus 7th, where the minus sign means the number is very small, and the number 7 means there are 7 numbers behind the decimal point. So if we need to deal with a number that is very small, we can write it as 3 times 10 to the minus 7 in this case. Finally, there are sometimes you will see a number that I wrote with a twiddle sign in front. So the twiddle sign here means approximately, or about 3 millions in this case. It means that the actual number could be 2.91 millions or 3.37 millions, but it doesn't really matter. I'm going to call it as 3 million or approximately 3 million to make my life easier. All right, cool. So now let's start with the weather on Earth. The Earth is surrounded by its atmosphere that everyone knows. The radius of Earth is 4,000 miles. In scientific notation, as we just learned in the previous slides, we can write the number as 4 times 10 to the 3. For the atmosphere, the thickness of the atmosphere is about 300 miles, so this is less than 10% of the radius of Earth. Our human activities actually only occur, or usually occur, within 10 miles from the ground. So this is a very small fraction of the volume that we are talking about here. And in the Earth atmosphere, there are many weather conditions that we have experienced on daily basis. For example, we have seen, or we may see, rains, winds, thunders, and clouds. Unfortunately, I live in California, so we don't really get that much rain or thunder. And that's something I miss because I grew up in southern China, where typhoon is very common. And I remember in late August to September, which is when we have this talk right now, in my hometown, we will get downpouring rain almost every day. So that's definitely something I miss. How does the weather look like in a galaxy? Usually when we think of a galaxy, we are imagining its visible part of the galaxy, meaning that the lights are coming from the stars in the galaxy. And those stars are certainly very exciting, and I bet you have seen many beautiful and stunning images of the stars in different types of galaxies. But tonight, I'm going to tell you something else that we cannot usually see with our optical telescopes or naked eyes. Some of you may have heard about this term, which is dark matter, or some of you might feel excited right now because I mentioned dark matter. Dark matter is used to describe the matter that is invisible, and we can only feel the existence of the matter through gravitational interactions. So it turns out for a galaxy like the Milky Way, the galaxy has a huge dark matter. Let me give you some numbers here. The size of the galaxy, the visible part, or the part we can see the photons, the visible light, is about 100,000 light years across from one end to the other end. For the size of its dark matter halo, it could be 10 to 20 times bigger. So this is about 2 million light years across. This is saying the dark matter halo of a galaxy could be much bigger than the visible part of the galaxy itself. So next time when you think about a galaxy, think about the dark matter halo that's surrounding it, which has enormous amount of volume and it occupies a huge space. All right, so the numbers here are again too big, and it's difficult for us to remember how big the dark matter halo is. I'm going to imagine I or the superwoman, and I can squeeze everything into a basketball. So now I'm going to scale everything down to the size of a basketball, which is manageable. In this case, the galaxy in the center, or all those stars in the center, will only occupy a space that is as small as a dime. So we are talking about a basketball as a dark matter halo, and we are talking about teeny tiny dime in the center, and that is the optical or visible part of the galaxy that we usually see. So in other words, the volume of the dark matter halo is much bigger than the volume of the luminous parts of a galaxy. Now let's come to the topic tonight, the galactic weather, or the cycle that I do my research. The clouds, the rains, and the winds that we hope to see and learn that happens in this dark matter space, that is the topic tonight. Here is an artistic illustration of the galactic weather that we might see in the galaxy's dark matter halo. Different colors shows you different weather station. So basically what you are looking at here is, first of all, in blue, you are looking at inflows coming into the galaxy, and those are mostly hydrogen, and I'll show you the chemical composition later on. Then in red and brownish color, we will find galactic winds rushing out of the galaxy, and those are winds carry enormous amounts of gas and energy from the galaxy into the dark matter halo of the galaxy. This is very similar to the volcano eruption on Earth, where lots of ashes and dust are thrown into the air and floating around. And those volcano eruptions first move upward, and then they're being dragged down to the ground because of the gravity of the Earth. In the galaxy's dark matter halo, we can see a similar process here. As the galactic winds move away from the galaxy, the gravity of the galaxy is kind of saying, no, don't move away, so the galaxies start to drag the material down. And this is a process we call recycling. Basically, if the wind is not powerful enough on the material, will start to rain back down to the galaxy, and it will be recycled back to the galaxy again. So altogether, the inflow, the galactic winds, and the recycling form the galactic weather system. And these three conditions are not mutually exclusive, meaning all of them can happen at the same time in the galaxy, and they are actually interacting with each other, which I will show you in a video later on. So this is very much like the weather on Earth, that it could be sunny for me today, but at the same time it could be raining for you if you are in a different place in the United States or in other country as well. All right, so to understand the weather system, astronomers have been using different kinds of telescopes to observe the galaxies in the universe. So I have mentioned optical telescope before because those are the telescopes we use to observe the stars in the galaxy. But here I'm going to show you three different kinds of other telescopes that we don't usually use to observe optical objects. So they function in different wavelengths. So first of all, let's take a look at what's going on in our backyard, the Milky Way. And you are looking at the Fermi Bubbles, which were observed by NASA's Fermi Space Telescope. And so Fermi Space Telescope operate in the gamma ray emission wavelengths, and I'll tell you what gamma ray is in a little bit. In this image, the horizontal feature is the Milky Way galactic plane, and sometimes we can see the Milky Way galactic plane with our naked eyes if we are in a place that has not as much city light. So there are stars, dust, and gas in the Milky Way's galactic plane. Our solar system, i.e. where we are here, is about 26,000 light years away from the center of the Milky Way. And so this is like a huge distance across. The most prominent feature in this image is actually the two Fermi Bubbles extending above and below the galactic plane. And in total, they extend over 50,000 light years across in total. And you see slightly different color here in magenta and pink and in blue. You are looking at the gamma ray emission and the X-ray emissions. So these gamma ray emissions are created because of the very fast-moving energetic electrons crash into low-energy photons. And in this case, they generate an energetic gamma ray. That's what we see in magenta here. Why we see these high-energy energetic electrons, we don't know. So that's something astronomers would like to know with more research and observations in computer simulation. Now let's move on to other phenomena in the Milky Way. We can also observe things like the Magellanic String. So in this figure, you are looking at the large and small Magellanic clouds. So if you are in the southern hemisphere, for example, New Zealand, you can see the large and small Magellanic cloud with your naked eyes, actually. So those are the two stunning features on the sky. I've never been to the southern hemisphere, so I would absolutely like to see them at some time. So both the large and the small Magellanic clouds are at a distance about 160,000 light years away from us. The Magellanic String, which is in pink here, originated from the large and small Magellanic clouds, and the hydrogen in the string carries a large amount of weight. It is about 0.3 billion solar mass. Again, this number is too big. And here the solar mass means the weight of the sun. This hydrogen might eventually be merged into the Milky Way plane in the future. So that is the future galactic weather we astronomers are looking forward to in a few billion years. And normally, hydrogen gas doesn't really glow in optical light. So astronomers use telescopes that actually can receive photons in radio frequency to observe this gas. And for example, this is the Parkes telescope in Australia that we can use to observe the Magellanic String. The phenomena in our own Milky Way. Now let's take a look at one of our neighbors, the Cigar Galaxy. So the code name of the Cigar Galaxy in astronomy is M82. The Cigar Galaxy is about 12 million light years away from the Milky Way, so it's pretty far away, but we can still see the very stunning feature from the galaxy using the Hubble Space Telescope. And the Cigar Galaxy is forming stars at a much faster rate than the Milky Way itself. Here you are looking at the red color, which are hydrogen clumps glowing in infrared light. And they are materials blown away from the galaxy and carried by the powerful and energetic galactic winds. These are materials that have high-speed winds and carry tons of energy and weight. Now, on the other hand, in blue and brown color, there are stars shining in optical light. This image of the Cigar Galaxy was released actually in 2006 by NASA and the European Space Agency to celebrate the 16th anniversary of the Hubble Space Telescope. And this is a mosaic image, meaning at the beginning when Hubble took these observations, it took it with 4 different filters. And then astronomers combine images from different filters together, and eventually we see different features from different filters. That's why the image is so stunning and so beautiful now. In addition to telescopes, astronomers have been using very powerful supercomputers in recent decades to understand how the galaxy like the Milky Way form and evolve as well. And also, supercomputer is a very powerful tool to understand how a weather system can change in the galaxy's dark matter halo from time to time. Now let me show you a video because we have been looking at a lot of images so far. And this video was made by NASA AMS, and it is highlighting a recent research result by a simulation team called Foggy, which is short for Figuring Out Guessing Galaxies in Enzo. Let me play the video. In a simulation, first, we are looking at a very small volume of the universe when the universe was very young. At that time, galaxies looked very small, and they were interacting with each other very actively. Some galaxies end up merging with each other, so they become a bigger galaxy. Now pay attention to the greenish color here. They are mostly hydrogen gas, and they flow towards the galaxies, feeding the galaxies, so the galaxies will grow bigger and bigger in sizes and weight. Sometimes you see red stuff being blown out of galaxies in very energetic ways. So those were galactic winds that we were talking about some slides ago. So those are galactic winds driven by star formation activities, and they have populated the universe with all different kinds of elements that were produced when the stars are formed. Okay, now let me play the video again, now that you know what to expect. Okay. Again, just quickly, you're looking at a very small volume at the very early time of the universe, and the galaxies started in very small sizes, and they interact with each other and merge with each other to become bigger galaxies. And in this process, you see hydrogen inflows, which is in greenish color, and you see very powerful galactic winds, which is in red, and they are interacting with each other. So eventually you will see a beautiful spiral galaxy rotating in the center of the video, and that is kind of what our own Milky Way looks like. So the goal of this research is to design a simulation that can help us understand what's going on in our own Milky Way's weather system. Alright, so with telescopes and supercomputers, astronomers are able to measure the properties of the gas in the galactic weather system, such as the chemical composition, wind speed, and temperature. Now I'm going to compare the numbers measured for the weather system on Earth to those observed for the weather system in the galaxy. You will see that the numbers are very different from each other. First of all, chemical composition. On Earth, in the atmosphere, there is about 78% of molecular nitrogen plus 21% of molecular oxygen. The rest 1% goes into other molecules such as water vapor and carbon dioxide. Now let's take a look at the chemical composition in the galaxy, or let's say everywhere in the universe. There are 3/4 of hydrogen by mass and 1/4 of helium. So the 3:1 ratio of hydrogen to helium was originated from the Big Bang nucleosynthesis. And this ratio has been the same almost everywhere in the universe. In other words, if we were able to hop from one galaxy to another galaxy and from, say, our solar system to the center of the Milky Way, we will find a similar hydrogen to helium mass ratio, which is about 73% to 25%. For the last 2%, they include other elements such as hydrogen, oxygen, and nitrogen. These are the elements that were produced in star formation process. All right, weight of gas. Okay, now we're dealing with something very big. I'm going to use a unit called 1 Earth mass. And you will see very soon why such a unit is necessary. So 1 Earth mass equals to 1 times 10 to the 25 pounds, actually a little bit more than that, but I'm going to use an approximation here. Again, in scientific notation, 25 here means there are 25 zeros behind 1. For the atmosphere on Earth, the weight is about 1/1,000,000th of Earth weight. So basically, the Earth atmosphere weighs very, very little in comparison to the total weight of the planet. For gas in a galaxy's dark matter halo, in particular, for a galaxy like the Milky Way, the total gas mass could be 3 times 10 to the 15 of Earth weight. So this is something that is much heavier than what we can deal with on Earth, but our galaxy is powerful enough to do so, to carry the weight of its own weather system. Cool. Wind speed. On Earth, some of us have to deal with hurricane season, like from time to time, and every year. I'm going to quote the hurricane category decided by the National Hurricane Center and the Central Pacific Hurricane Center. How about the winds in the Galactic Weather system? Astronomers so far have measured a wind speed that can reach about 0.2 to 2 million miles per hour. So this is something too big for us to imagine. So I decided to put it in the category infinity here. Now let's move on to precipitation rate. On Earth, when we talk about precipitation rate, we mean how much rain we can collect over some amount of time. For example, if it's raining outside today and I want to measure the precipitation rate, I will put the container outside to collect the raindrops. Although, unfortunately, I live in California, so I believe some of you live in California as well, and unfortunately, we don't get that much rain. Anyway, let's imagine if it rained and we put the container outside. Sometime later, it could be 1 hour, 1 day, 1 month, or a year. Let's take in the container, and then now let's measure the height of the water level from the bottom of the container to the top of the water level. So that height in inches tells us how much rain have been collected over the amount of time that the container was put outside. With this method, now let's take a look at some data. In the Bay Area where there hasn't been that much rain at all in recent months, the precipitation rate is about 0 inches. Kind of sad. On the contrary, in this chart, we are looking at the precipitation rate in Florida, where you can see from 1895 to 2009, everywhere they are getting about 54 inches of rain every year on average. How about the hydrogen rain in the Milky Way? Basically, every hour, there are 5 times 10 to the 26 pounds of hydrogen pouring to the galactic plane. I use pounds here instead of inches because there is no container so big for us to use to measure the rain level in height. This is a number equal to 38 Earth weight per hour. For astronomers, we use a much bigger unit so that this number would look smaller. So we say the precipitation rate in the Milky Way is about 1 solar mass per year. So that's the number we would use in our research. All right, temperature. This is something I found very interesting. Let's take a look at the temperature in a city, for example, Chicago. This is the temperature in Chicago in early August. At that time, the temperature was about 60 to 90 Fahrenheit. And this number is very small compared to what we will see in the galaxy. So to prepare you for the astronomical numbers that will come up in a little bit, let's start with something that's less dramatic. First of all, if you want to melt a glass cup, we need a temperature about 1400 to 1600 Fahrenheit. Just to be clear, glass doesn't really have a fixed melting point, so you could use a higher temperature or a lower temperature to melt a glass mug, a glass, depending on the material specifically. On the other hand, if you have a car that's fully made of ions, you need a melting temperature of 2800 Fahrenheit. So this is much higher already. If we're able to go into the interior of the sun, the temperature there is about 10,000 Fahrenheit. So basically, everything will be on fire if it's close to the sun, and we will not expect car, glass, or any kind of things we can see on Earth to still exist in the interior of the sun. How about the temperature of gas in the galaxy's dark matter halo? For the inflow in blue, here the temperature is about 10,000 kelvins. The Kelvin is a temperature unit that physicists and astronomers like to use a lot. It's approximately 17,000 Fahrenheit. For the high-speed, powerful winds, the temperature can reach 1.8 million Fahrenheit or even higher. Again, everything will be on fire if they were in this kind of galactic weather system or this kind of environment. And the elements will exist in their most basic form, which are atoms instead of molecules or compounds that we would commonly find on Earth. Now let's take a look at the density. The density is something that can tell you how packed things are in the space or in the volume. For example, for a can of sardine, the fish, the density of the fish in the can could be very high. That's why we use a can of sardines to sometimes describe the subway cars in New York City. On the contrary, for a bag of potato chips, the total number of chips you can find in the bag could be disappointingly low. So that is the situation. We would say the density of the chips in the bag is very low. All right, in the Earth atmosphere, there are 2.5 times 10 to the 19 molecule per centimeter cube. Centimeter cube is a unit that some of you might not be familiar with, so let's walk through it together. Think about the sugar cube in your kitchen. It's about this big. And 1 centimeter cube is about 1 fraction of your sugar cube. So it's like smaller. 1 centimeter cube is smaller than 1 sugar cube in your kitchen. And this number is telling us that there are a lot of molecules in the air floating around, even though we don't really see any of those with our naked eyes. To give you an example, the vacuum cleaner that I use at home can create a vacuum environment with a density that is about 1 times 10 to the 19 molecule per centimeter cube. So this is a factor of 2 less dense than what's going on in the air. And so for a vacuum cleaner to work efficiently, we only need to reduce the density by a factor of 2. For the air on the moon, there are about 3 times 10 to the 5 particles per centimeter cube. And this is an environment with such a low density that human beings actually cannot live there without any kinds of protection. How about the gas in a galaxy's dark matter halo? Anyone wants to guess here? I'm going to wait for 2 seconds. Okay, so in the galactic weather system, the density is about 1 times 10 to the minus 1 to 1 times 10 to the minus 5 particle per centimeter cube, or we can say it as 0.1 to 0.00001 particles per centimeter cube. This is saying for every centimeter cube, we cannot even find 1 particle in it. Now let me use an analogy to help you understand how low this density could be. If on Earth we can reach such a low density, say the fridge in your kitchen. If the kitchen has such a low density, it means when you open your fridge, instead of finding produce such as vegetables and fruits in it, at such a low density, there would be 1 teeny tiny particle in the whole fridge space. And the size of the particle is much smaller than the size of your hair. So that's a low density space we're talking about when we study the galactic weather system. Finally, let's talk about how quickly things can evolve, which we call the timescale. For the weather system, a timescale means how quickly the weather change from one condition to another. For example, from partially cloudy to sunny situations. I'm going to show you a weather forecast in August for Clemson. From Thursday to Friday, the weather changed from partially cloudy to rainy, and then on Saturday, it turned partially cloudy again. Therefore, we can say weather on Earth changes over a timescale of a few hours to days. Some of you may experience more extreme weather systems that are, for example, strong winds, hurricanes, in which cases it could last for a few days or month. How about the weather in the galaxy? As I started at the very beginning, our Milky Way and other galaxies that are similar to the Milky Way have experienced all kinds of weather. For example, clumpy clouds, hydrogen rains, strong galactic winds, and other like recycling process. This phenomenon happens over a timescale of millions to billions of years. So it's very long, and it's certainly something we as humans cannot keep track of because of our short lifespan. But we can use powerful telescopes and supercomputers to piece all different kinds of information together to understand how a galaxy's weather system change from time to time. We've gone through lots of numbers, and I'm actually getting tired, and because remembering these numbers require lots of space sitting here. So that's actually not practical because those numbers are either astronomically too big or astronomically too small. Instead of remembering these numbers, the message I would like you to take away from the talk tonight is that a galaxy has an atmosphere just like Earth has an atmosphere or the Sun has a corona. And sometimes we do call the galaxy's weather system as the galactic corona. And the galactic weather system is heavy, but it is very low density. It has a complicated weather system with gas that is insanely hot, and the gas is moving around very fast and interacting with each other. These weather conditions had occurred in the past million to billion years, and they are happening now, and they will happen again and again in the next billion years. So that's something we astronomers are looking forward to, and that's something we wanted to study. Now I hope all of you have become experts of galactic weather. Now let's look at another video. This video zooms into the inner region of the galaxy, and it highlights how different galactic weather conditions can interact with each other. First of all, on the top of the video, you are looking at a huge blob of hydrogen pouring down. Just imagine it as a huge bucket of water poured down from your neighbor's balcony. And this gas has relatively low temperature. In the bottom, you are looking at galactic winds in yellow and in gold color, and those are galactic winds launched by star formation process from the galaxy into the dark matter halo of the galaxy. And they are very hot, and they will rise upwards, and they will destroy the downpouring hydrogen rains, which you will see in a little bit. All right, now let's play the video. So you see that as the hydrogen rains in purple pouring down, it gets dissolved into smaller clumps and smaller structures. In a few seconds, you are going to see a huge galactic wind being launched from the bottom, which will push everything upward and destroy the hydrogen rains. This video is telling us different galactic weather conditions can happen at the same time, and they are not mutually exclusive. and different weather conditions interact with each other very closely. All right, now that you know what to expect of this video, let me play it again and see if there are other details you might have missed. Again, from the top, there is a giant blob of hydrogen rain pouring down. And this blob of hydrogen rain will be met with the powerful energetic galactic winds, and they will interact with each other, and you will see interesting clumpy and filamentary structures. All right, cool. That's all I wanted to share today, and we have gone through lots of numbers and new concepts. And it may seem overwhelming because these numbers and concepts are sometimes difficult to remember. So let's do a quick recap. We started with a galaxy, and I show you only the luminous part of the galaxy, which are mostly stars in the galaxy. And then we move on to the dark matter halo of the galaxies, which could be 10 to 20 times bigger than the luminous part of the galaxy disk. In this dark matter halo, there is a very complex weather system where you can find hydrogen rains, galactic winds, and recycling process. And all these things together form the galaxy's Baryon Cycle, which is the research subject that I am interested in at UC Berkeley. Finally, the ultimate questions for me and for everyone is, why do we care about the galactic weather and why I spend so much time on it? So my 1 minute elevator pitch answer would be, the galactic weather, the inflows, winds, and the recycling closely connect the galaxy to its dark matter halo. So by moving gas or hydrogen in and out of a galaxy, between the galaxy and the dark matter halo, the galaxy can keep forming stars and can be alive for a long period of time, like over a time scale of billion years. All right, thank you everyone. And this presentation was made possible with the help of the internet and my colleagues. And big shout out to artist Michael Blonsky for discussing many aspects of this presentation. And that's the end of my talk, and thank you for your time, and thank you for listening, and you are welcome to ask any questions you might have.
I hope you enjoyed watching Galactic Weather with astrophysicist Yong Zheng of the University of California at Berkeley. These programs are produced by Mount Tam Astronomy in collaboration with the Friends of Mount Tam, with the San Francisco Amateur Astronomers, and with Wonderfest, the Bay Area beacon of science. The programs are free and open to all. Mount Tam Astronomy is organized by Tinka Ross, and this video was produced by John Navas. To attend a live program, followed by live telescope viewing of the night sky, or for a list of upcoming Astronomy Nights programs, visit our website at mounttamastronomy.org. For Mount Tam Astronomy, I'm Tucker Hiatt.